Oh, okay,
Yeah, we do.
sorry for that. As I was saying, I'm Pol Garcia. I'm glad to be the icebreaker, so I'll try to set expectations as high as possible for the rest of the colleagues. I would like to present the Deep Chess project alongside with my colleagues Sergi Sellés, Sergi Parera, Borja Garcia, and our advisor Dani Fojo, which I believe he's not here, but anyway. Okay, I would like to start with the motivation of the project. In the end, this project combines two different things, which are chess and reinforcement learning. On the one hand, chess is known to be one of the most emblematic games in the history of humanity, when it's being simple and complex at the same time. And on the other side, reinforcement learning was actually really attractive to us. And besides that, it also provides a lot of documentation because there has been a lot of research being done already for this field, and that provided us a very solid baseline so as to build things on top of it without assuming any major risk. If we jump to the next slide, we can see here our hypothesis. I would like only to highlight two things here. The first one is that the only unchecked goal you see, it's not that it has been a failure by any means. It means that we have had no time to test it and to provide reliable results. So as we decided to discard it from the list, that's all. And the second thing I would like to highlight is that the last goal, as you can see, is double checked. This was actually really important to us because it started being an internal safety check, since you know, and chess is kind of a complex environment. So one of our safety checks was to extrapolate our algorithm into a simpler environment so as to check if we were doing things right or it was something else beyond our comprehension that was failing. So in the end, we started scaling these simpler environments into more difficult environments, and the algorithm was behaving really, really well. That's why I actually double checked that, and we wanted to make sure this was being shown in our presentation because it was really, really interesting for us. Okay, we can go to the next slide. I'll try to be really quick with this because it's not really that important, but I would like to provide a bit of a brief introduction to reinforcement learning. Here, I would like to highlight the Markovian decision process, which is a mathematical algorithm that actually plays in partly random environments, which fits perfectly with chess, because in chess you have one movement, it's being done randomly by the opponent, which you cannot foresee, and the other move, it's actually under your control as agent of the environment. So this framework works with states, actions, rewards, and probability distributions. And it's actually, the focus is put on the learning. I mean, we're not going to teach the algorithm how to act, but we are actually teach it how to know how to act at each state. So it's more of a decision-making rather than learning process. We can go to the next one, Borja. As you can see, our model, or almost every reinforcement learning model, consists of two components, which are agent and environment, that they exchange things. The agent is passing actions to the environment, and the environment sends back as a new state with a new reward assigned to it based on how good or bad this action was. So the goal here is to maximize the overall reward of the agent. Next, please. Thanks. Okay, very quickly here, it's just our final project plan. I just want you to focus in the algorithm enhancements module, because this was, trust me, this was really game changing. So this actually boosted our performance drastically in the model, and it was identified right after the critical review presentation. I will explain in a second what it consists of. We can go to the next one, please. This is the workflow of our algorithm based, from a functional standpoint. So I will not explain any technical details here because they will be explained afterwards by my colleague Borja. But I just want to provide an overview on how we made our algorithm work in terms of functionalities. So starting on the top left corner, we can see the new board position, or a new state. That from this state, we actually try to foresee or identify all the possible moves that can be made by the agent. To each of these moves, we assign a probability distribution to then pick the move that has its highest probability. To pick a move means to actually execute an action in a chess game that actually leads this algorithm to a new state. Okay, then once we've reached this new state, we actually check, okay, is the game over? If it's not, we pass this state back again to the whole loop. And if it is yes, we just assign a reward to this agent based on if it has won or lost the match. or the game, and then we propagate everything and we try again with a new position or a new game. You can pass to the next one, please. Okay, and this is the enhanced algorithm workflow. What I was saying about before about game changing our project. You can see it's slightly tweaked, the workflow, but I want you to focus mainly on the three yellow squares that you can see. I'm not gonna get into technical details with them, but I just want you to provide an idea on how we approach this. I mean, what we were aiming with these enhancements. And basically what we were targeting is that preventing the algorithm from doing too much unnecessary work so as he can focus on learning quickly and learning well. So in the end, as a summary, we just prevented the algorithm, for example, from processing illegal moves. So we masked out all these illegal moves so as he could focus on the legal moves, which is the vast minority of the moves possible. We also prevented the algorithm, for example, to reassess movements that had been done in the past with with an identical score. So we were saving the algorithm this training load. And we also provided the algorithm with an external evaluator that actually provides an objective score on each of the moves, so as it can be translated into human language of scores. And I think that's it from my side. I will pass it to Borja, and he will explain this exact same thing, but much more in detail and technically speaking. So Borja, all yours.
Okay, hello everybody. So first of all, I will explain our training idea, which basically is to have the machine play against itself. Then if the movement it makes is bad, we will penalize the agent. If the movement it makes is good, penalty will tend to 0. If we reach a checkmate position, we will reward the agent, and we will train this until our average reward reaches value greater than a certain threshold, and then we will consider training is finished. So I will explain now with a bit more of detail our pipeline. We start with chess position and we convert it to a tensor format our neural network can understand. This is fed to the neural network, which will output our policy distribution from which we will sample an action. And after executing the action, we will get to a new state and compute a reward for our agent. Here we will check if the episode is finished, in which case we will compute the gradients and update neural network parameters and start the process again. If not, we will feed the new state back to the neural network and keep going like this until we reach a terminal state. So regarding our chess environment, it's basically implemented with a Python library called Python Chess, which has everything we need to implement the chess games. And our initial positions are basically 20% of times initial chessboard position, 80% of times special tactical positions. The initial chessboard teaches the algorithm how to play in the beginning and in the mid game, and the tactical positions aim to teach the program how to finish the game. These positions are taken from a huge data set from lichess.org. It has more than 1 million positions. So now I will explain how we convert from our chess environment to something our neural network can understand. And this is basically done. Our chessboard is encoded with a tensor 33 times 8 times 8. 8 times 8 is the size of the chessboard. So basically we are using 33 chessboards. Boards 0 to 5 encode where each of the white pieces are. For example, you can see all of the white pawns are marked in red, and this would be this board shape. Knights are yellow, and you can see their position here with a 1. Bishops are blue, and so on and so forth. Then boards 6 to 11 show which squares are white pieces attacking. Again, if we look at the pawns, they would be controlling the entire third row, which is you can see in this 8 by 8 board. And the knights would attack these yellow squares, which is also represented here. Then we have boards 12 to 23, which basically do the same I just explained, but for the black pieces. And finally, boards 24 to 32 encode other chess features on which basically the entire board will get the same value. An easy example of this is the side to move. When blacks are to move, the entire board will be 0. When whites are to move, it will be 1s. Now I will explain how we pass from the output of our neural network to something Python chess can understand and how we sample an action. And the first thing we need to understand is the movement encoding. Basically, the idea is to pick a piece in one square of the board, which is 8 times 8, and leave it in another square of the board, which is also 8 times 8. So basically, we are going to have 8 times 8 times 8 times 8. It's 4096 possible moves, and then we have 176 special ones that are the promotions. That is when a pawn reaches the last row of the board and it's promoted to queen, rook, bishop, or knight. And normally the pawns move straight or diagonal when they make a capture. So a total, if you do the math, you will get 176 possible promotion moves. Each of these moves is encoded with an integer number. And then Python chess, which is basically our environment, uses a string in order to code each of the movements. So in order to map from one thing to the other, we use a Python dictionary. So the way all of this works is our neural network outputs 1 times 4272 tensor, which is all of the possible moves in logit shape. Here we mask out all of the illegal moves. This is something that the neural network can actually infer, but in order to speed the training, and also it's something that the state-of-the-art programs are doing, we decided to mask the illegal moves out. So after this, we take the logits and convert them to a categorical distribution. From this distribution, we sample an action, and with our dictionary, we move to something Python chess understands, and we move. Now, let me explain how we reward our agent. This is done basically every single time we make a movement. We used Stockfish engine, which is a chess engine that outputs a scalar value depending on how good or bad the chess position is for white or for black pieces. And the idea behind this is that if the movement is good, this number here will not change much, so the reward will tend to 0. If the movement is bad, reward will change. There will be a change in the reward, and then this value will be negative, and we will penalize the agent. On the other hand, if we reach a checkmate position, which is what we want in chess, we will reward the agent with a +1. Now, a little bit, I will explain quickly the main problems we have had with this environment, which is that it's quite slow because our model and our neural network are on the GPU, but Python chess and Stockfish are executed on CPU. So in order to overcome this important limitation, we use Python multithreading and hash table in Python. The hash table basically tackles the problem that Stockfish by itself, it's quite slow. So what we do is that every single time we find a new position we have never seen before, we call a Stockfish. It evaluates the position, and we store both the position in orange and the evaluation value in blue, so that next time we see the very same position, we don't need to call Stockfish, but just recover the value. And on the other hand, multi-threading was used in order to accelerate experience collection in order to create a batch for our model. So basically what we do is in one single PC, we run many games at the same time with one GPU. And once that we have collected enough experience, we create the batch and training in our GPU. And finally, a quick overview of the architectures we have used for our models. We started with a convolutional neural network and multi-layer perceptron, with which we managed to memorize movements, and the algorithm was able to repeat the same games over and over again as soon as it found a quick way to get to the reward. But after seeing how other state-of-the-art programs were doing this, we noticed that everybody was using ResNets and that we would use something more powerful. We tried after that many different architectures for ResNets, and in the end, the best compromise between speed and performance was to use one ResNet with 2 heads, one for the policy and another one for the value, which it's basically the expectation over the future rewards. And yep, this is the overview of our chess implementation. Now I will hand over to Sergi, who will explain the different algorithms.
Yes, hello, this is Sergi Sellés. So I will explain about algorithm evolution. So as a first step to build our chess engine, in order to learn how to implement reinforced learning, we start with the policy gradient and DQN algorithm that were already explained in this course. Then we implemented PPO, which is recognized that has better performance. And at the same time, it was new for us, so we have to make effort to learn about it. With these implementations, we have tried to solve basic environment, firstly, like carpol, same as we did in the course, but then also we face other more difficult binomials like Lunar Lander and Mountain Car. And finally, of course, we face chess that is far more complex than any of these environments. So additionally, we have used supervised learning to try to solve the problem of chess. So next slide, please. Okay, so I will just make a comment about policy gradient. We use this algorithm because it's the baseline for PPO, so it's a good start to learn about reinforced learning. It's a policy algorithm. We interact with the environment using the actions proposed by a policy net. We train this policy net with the collected rewards using gradient descent, as this is same as we made in the course. So the policy gradient, what we learned from it is that it memorizes legal moves and entire games as soon as a quick way to reward is found. So this was our first step. Second step is about DQN. We implemented this algorithm just to remind that it has two policy net, one trained online and another offline. The loss function is a mean square error of the difference between a Q value that is calculated with the online policy and a TD target that is calculated with the collected rewards and the offline policy. After several epochs, the parameters of the offline policy are updated with the ones from the online policy. This is the same as we did in the course. So DQN served also to initially test the chess environment that we created. So it proved that it works. With DQN, we tried to train the policy to generate legal actions, but the learning rate was too slow. And after several hours of training, we got just about 10 legal actions. So we just learned that same as other chess engines like AlphaZero, it's better to mask out the illegal action from the policy net and to train only to generate high rewards move. We knew PPO has better performance than DQN, so we concentrate our efforts on PPO. So I will let Sergi to explain the next. Thank you.
Okay, so I will explain about PPO. It is also a non-policy algorithm like policy gradient, and it works for continuous and discrete actions. And the good thing about PPO is that it limits the step size or how the network changes where it finds a good action. So the step is not too far away that it actually worsens the net. And this is the objective function of the PPO algorithm, that you can see that there's a part of clip that I will talk about later. Okay, this is the more or less a really simple schematic of the algorithm and how it works. And first, you have to collect episodes simulating your environment. And this can actually be less than the length of the environment. You don't need to collect a full environment or a full simulation. Then you compute the rewards and an advantage function that it's a value that tells you how good the action was compared to the rest of the actions or the distribution of actions. Then you compute the actor and the value loss, and this is where this algorithm is really different, and it's the equation that I told you before. The value loss, it's only a mean squared error loss between the rewards and the predicted value of the action. But the actor loss, it's more complicated than that, and it's where you limit the change. And as a general idea, if the action is good, you will apply a limit in order not to end up performing worse. And this limit, it's by limiting the ratio between the logarithm of the action probabilities like before and after. If you have any doubts, I will explain later, but we don't have time to enter this now. And then you update the policy with these losses that you calculated. And actually you do this more than once without running more episodes. And this is proven in the paper, the PPO paper made by Google or OpenAI, that it's the state of the art, basically. Okay, next. And as Paul tested, as Paul said, we tested this in other environments rather than chess that were simpler environments, so we could check this, that it was working. So we tested this in Carpol, that you can see on the screen. Then we tested it in Lunar Lander, that it's a more difficult environment, and it also worked perfectly. You can see some GIFs here. And then we tested in the mountain car environment, which is more difficult because it doesn't give any reward until it's completely done. So the algorithm doesn't have any clue if it's doing it right or wrong. So it has to start exploring by itself. And then we tried in chess, and here is where we found out that something was not completely right, because it was not learning as we expected to be learning. And well, we extracted some hypotheses that my colleague Sergi will talk about next. Thank you. Oh, sorry. Yes, after that, we tried supervised learning to learn how to play chess, because reinforcement learning didn't work. So we tackled this as if a form of image recognition. So you give a state and you output a move. So it works like this. We just train it as we have seen in class for the image recognition. Next slide. And we tested without the back propagation, and the results were really satisfying, because we found out that it learned how to play chess, this one. And if we played a random simulation against a random player, it win 11 times out of 20. It never, well, it did not lose. It had 4 rounds and 5 timeouts. And this GIF is one of the games that it won.
Okay, so I think we run out of time, so I will skip evaluation slide, this one and the next. Okay, so I will comment about results. So for policy gradient, I will summarize results for policy gradient. As we mentioned, and DQN, we make just initial learning of this project. With PPO, this is the start of our project. We were able to solve Carpol, that is easy, but Lunar Lander mountain car is more difficult. And then we learned that PPO, our algorithm, is well implemented. With supervised learning, on the contrary, we were able to achieve some chess knowledge, and we were able to beat a random move player. That is one of the key targets of our project. For PPO chess, as comment, we found that is too slow progress in training chess. And then when we compare with other state-of-art algorithm, we understood that it requires to implement from our side an additional module that is a tree search strategy, a Monte Carlo tree search. So next slide, please. So the comment is that, yes, Monte Carlo tree search at first, we thought that was not necessary because we had a reward scheme different from others. So typically AlphaZero and others, they don't provide reward until the end of the play. On the contrary, in our environment, we are able to provide a reward at each action. So finally, chess complexity is so huge that we need to have a tree strategy. So then we prepare a Monte Carlo tree search module to make training of our PPO chess, but we had no time to complete the run. The next slide, please. So as a conclusion, and just as a summary of our activity, when we started our targets, the algorithm works. So yes, we can say the algorithm works because the PPO algorithm is able to solve critical environments like a lunar lander or mountain car. Also, we learned that our algorithm is not just random, it aims to win. And this is something that, thanks to training with supervised learning, we were able to beat a random player and shows chess knowledge. And finally, one lesson that we had on this project is that to train our chess engine with PPO alone is not enough. We need a tree search strategy, a Monte Carlo tree search, to complete the job. So next slide. Simply say, if we had more time, we will continue PPO training with this module that is ready to run. And also because we know tree search has a big computer demand, so computer requirements has changed in our project. So we know that we will need something that can be provided like a Google Cloud platform. We have an instance prepared, but we had no time to put all together for the completion of this project. Okay, that's all from our side. Thank you for your attention.